Oxygen dissociation curve. What is the meaning of oxygen dissociation curve, or ODC? It's the plot in which there is a plot between saturation of the binding site with oxygen in hemoglobin or myoglobin on the y-axis, measured against the different partial pressure of oxygen PO2 on the x-axis. Myoglobin has a higher oxygen affinity at any PO2 value than hemoglobin. What is the meaning of higher affinity? This is the ability of myoglobin to bind with oxygen. So myoglobin is able to bind with oxygen released by hemoglobin at even very low pressure of oxygen found in the muscle, and in turn myoglobin release oxygen within the muscle in response to oxygen demand. So myoglobin, its main function is a reservoir. It's a reserve for oxygen, so it needs to have high affinity for oxygen released from hemoglobin in the muscle to bind with any amount of oxygen at any level, even very low levels of oxygen pressure in the muscle. So it can release oxygen in the conditions of the muscle demand. Oxygen dissociation curve in myoglobin, its shape is hyperbolic. This means that myoglobin binds to oxygen very tightly and release it at very low pressure of oxygen in the muscle demand, like what we said. But hemoglobin oxygen dissociation curve is sigmoidal shape. What's the meaning of sigmoidal? It's S-like shape. This means that hemoglobin have high affinity for oxygen binding at high pressure of oxygen, like in the lung. There is very high level of oxygen, so hemoglobin can bind to large amount of oxygen molecule. This means high affinity. And hemoglobin have low affinity for oxygen in low pressure of oxygen, like in the tissue. There is low pressure of oxygen, so hemoglobin has low affinity for oxygen, so it can release oxygen to the tissue, so it can mediate its main function, which is transportation of oxygen from the lung to the tissue, and we will explain this in details once more. Oxygen binding to hemoglobin show positive cooperativity. We said this before, like in this figure, that binding of one molecule of oxygen to hemoglobin will increase the affinity of other heme group in the same molecule to bind to more molecules of oxygen, more and more. This occurs due to conformational changes occur in the hemoglobin molecule. Deoxyhemoglobin, it's the T form or the tense form, have low affinity for oxygen, and oxygenated form or the relaxed form R form have high affinity of oxygen. This is the oxygen dissociation curve of both myoglobin and hemoglobin. Let's see the difference again. This is hyperbolic. This means that myoglobin have high affinity of oxygen binding at very low pressure of oxygen. This is the curve. Myoglobin have high affinity to bind with oxygen at very low level of oxygen. So it can reserve oxygen in the muscle and can give oxygen when the muscle need it. But hemoglobin curve, like what we see here, it's S-like shape or sigmoidal shape. It's the steepest level in its lower part where there is low pressure of oxygen. There is low pressure of oxygen, so the affinity for hemoglobin to bind with oxygen will decrease. The affinity decrease, but in high level of oxygen, like in the lung, the affinity of hemoglobin to bind with oxygen will increase. So hemoglobin in the lung have high affinity to oxygen, so it will be saturated with oxygen and will have oxygen from the lung. But in the tissue where there is low pressure of oxygen in the tissue, in this part, the hemoglobin will have low affinity. So it has low affinity to bind with oxygen, so hemoglobin will release oxygen to the tissue. And this is the main function of hemoglobin, is to have oxygen from the lung where there is high pressure of oxygen and release it in the tissue where there is low pressure of oxygen. This is the difference between oxygen dissociation curve of hemoglobin and myoglobin. Myoglobin is hyperbolic, but hemoglobin is sigmoidal shape. So myoglobin not affected by oxygen pressure. It have high affinity to bind with oxygen even at very low levels of oxygen. The ability of hemoglobin to reversibly bind with oxygen is affected by allosteric effectors. We said this before, and now we will explain it in details. What is the allosteric effectors? Allosteric effectors means they are factors that affect binding of the hemoglobin molecule with the oxygen in a location other than the active site, other than the heme group. This is the meaning of allosteric. Okay, interaction at one site of the hemoglobin molecule affect binding of the oxygen to the heme group at other location on the molecule. So the effectors act on other location than the location of binding or the site of binding of oxygen to the heme group. This is the meaning of allosteric, and this definition or this suffix we will have it very common in enzymes. What are the allosteric effectors affecting binding of hemoglobin with oxygen? They are pressure of oxygen. We said that high pressure of oxygen will increase the affinity of hemoglobin for binding with oxygen, as we explained in the last slide. And there is positive cooperativity. Again, was the meaning of positive cooperativity, that binding of one molecule of oxygen to one heme group in the hemoglobin molecule will increase the affinity of other heme group in the same molecule to bind with oxygen, so it will increase. So the last oxygen bounded is about 300 times greater the affinity than the first oxygen bounded. The second effector is pH and pressure of carbon dioxide and 2,3-biphosphoglycerate. It's one of the metabolites from the glycolysis, and carbon monoxide. They are allosteric effectors. There is no allosteric effectors that affect binding of myoglobin with oxygen, as it's simple equation. There is no, and myoglobin binding with oxygen not affected by any allosteric effectors. Here, this is the oxygen dissociation curve with hemoglobin. This is the y-axis where there is hemoglobin saturation, and this is the pressure of oxygen. Here is the normal curve of hemoglobin saturation, and B50 means that the pressure of oxygen in which 50% of the hemoglobin molecules are saturated with oxygen. There are many allosteric effectors affecting binding of hemoglobin with oxygen. May lead to right shift of the curve or left shift, and we will explain what the meaning of right shift of the oxygen dissociation curve and what the meaning of left shift. Let's to remember this. Right means to give someone. So right shift means that hemoglobin will give the tissue oxygen. So it means oxygen unloading. It will release the oxygen to the tissue. So its affinity to oxygen will decrease. It's vice versa. Again, right hand, your right hand means to give. So right shift of oxygen dissociation curve means that hemoglobin will give its oxygen to the tissue. It will unload oxygen, and again its affinity to oxygen will decrease. Factors that make right shift of the curve are increase in carbon dioxide, hydrogen ion concentration, temperature, and diphosphoglycerate. Increase in hydrogen ion concentration means low pH, you know this, and hemoglobin, and we won't explain it in this lecture. Again, factors that cause right shift. What the meaning of right shift? It means to give. A hemoglobin give its oxygen to the tissue, so oxygen unload and low affinity for oxygen. Those factors are increased carbon dioxide, hydrogen ions means decreased pH, increased temperature or diphosphoglycerate. And in contrast, the left shift. What the meaning of left shift? You will remember it by left means to leave the tissue. Okay, so oxygen will leave the tissue, so hemoglobin affinity for oxygen will increase, and there is decrease in oxygen unloading and increased oxygen loading. Again, Left means that oxygen leave the tissue. So there is decrease in oxygen unloading, increase hemoglobin affinity to bind with oxygen, and this is the contrast of the factors that cause right shift will be decrease in carbon dioxide, decrease in concentration of hydrogen ions, what means that there is increase in the pH, decrease in temperature, decrease in diphosphoglycerate. Also decrease in the pressure of oxygen will lead to left shift, and carbon monoxide and the fatal hemoglobin. Carbon monoxide, there are extra factors, carbon monoxide, methemoglobin, and the fatal hemoglobin. All of them lead to left shift of the oxygen dissociation curve. Left means that oxygen leave the tissue. There is increase the affinity of hemoglobin to bind with oxygen, and there is increase oxygen loading, decrease oxygen unloading. If we remembered and memorize this figure, you will know and understand the next slides. So this figure will summarize to you the next slides and all allosteric effectors that affect binding of hemoglobin with oxygen. Oxygen dissociation curve shift to right again. The pressure of oxygen 27 correspond to 50% hemoglobin saturation, which is the red curve, and this is called P50 of hemoglobin. The rightward shift means that a higher pressure of oxygen is required to reach the same saturation of hemoglobin. Let's see this words. This is the red curve, the normal, and this is B50. What the meaning of B50? It means saturation of 50% of hemoglobin molecules with oxygen. In the normal curve, the pressure needed for P50 is 27. But in the condition of the right shift here, P50, it will need more pressure of oxygen to reach the P50 of hemoglobin. So the hemoglobin affinity for oxygen will decrease, and there is release of oxygen to the tissue. Let's see on the left shift. B50 will need low pressure of oxygen to reach the B50. It's the 50% saturation of hemoglobin with oxygen. So this will increase the affinity of hemoglobin to be saturated with oxygen and will decrease the release of oxygen to the tissue. This is the meaning of right shift and left shift. Again, what the factors? Increased temperature, increased carbon dioxide, hydrogen ions, 2,3-diphosphoglycerate. The left shift means that to reach the P50 we need less pressure of oxygen. This means that the oxygen will leave the tissue. Factors are the contrast, low temperature, alkalosis, decrease carbon dioxide, decrease hydrogen ions, decrease diphosphoglycerate, and extra factors, methemoglobin and carbon monoxide. The first factor, pressure of oxygen, oxygen loading and unloading. Pressure of oxygen in the lung is very high. This will increase the affinity of hemoglobin to bind with oxygen, leading to saturation of hemoglobin will be full and increased saturation of hemoglobin. When at the tissue where the pressure of oxygen is low, there is low affinity of hemoglobin to oxygen, so hemoglobin will release its oxygen to the tissue, and this is the main function of hemoglobin. On the same time, myoglobin is designed to bind with oxygen released from hemoglobin at low pressure. So myoglobin will bind to oxygen in the muscle and release it in the muscle demand. This is the oxygen dissociation curve in the lung, where there is high pressure of oxygen and high affinity of hemoglobin to bind with oxygen, and the saturation is nearly 98%. In the tissue where there is low pressure of oxygen, there is low affinity of hemoglobin to bind with oxygen, so it releases its oxygen to the tissue, and this is the function of hemoglobin. In the lung, oxygen binds to hemoglobin converted into oxyhemoglobin, and there is release of carbon monoxide and the contrast at the tissue. Bohr effect. Bohr effect is the change of the oxygen binding to the hemoglobin due to the concentration of what? Hydrogen ions and carbon dioxide. In the peripheral tissue, there is increase of hydrogen ions and carbon dioxide due to the metabolism. Hydrogen ions will increase and carbon dioxide released from the metabolism and converted by the carbonic anhydrase into carbonic acid, and this is converted into bicarbonate and hydrogen ions. When both increase, this will favor the T form of hemoglobin. Do you remember the T form or taught, or the tense, or deoxyhemoglobin? Deoxyhemoglobin, it will be the favorable form in the presence of high concentration of protons, hydrogen ions, and carbon dioxide. This is the equation, and lead to shift to the right, as we said before. Conversely, raising the pH or lowering the concentration of carbon dioxide or hydrogen ions will increase the affinity of hemoglobin to bind with oxygen, means that there is shift to the left, and this will favor or stabilize the R form, the oxyhemoglobin. So protons, hydrogen ions, are allosteric effectors. They lead to, when they increase, lead to right shift of the oxygen dissociation curve. High concentrations of proton and carbon dioxides in capillaries is observed more than or higher than the alveolar capillaries of the lung, where carbon dioxide is released in the expired air. The differential pH gradient, the pH is higher in the lung and lower in the tissue, will favor unloading of oxygen from hemoglobin at the periphery and loading of oxygen in the lung. Mechanism of Bohr effect. Why the Bohr effect occur? This occurs due to the protons, the presence of protons, which will stabilize the T form Why it stabilizes the T form? As we said before, the T form, there is many ionic and hydrogen bonds between the two dimers of hemoglobin. These protons will cause ionizable groups like specific histidine side chains. These ionizable groups will favor stabilization of the T form or the TOT form or the deoxy form of hemoglobin, leading to decrease the affinity for oxygen binding and right shift. When protons decrease, this will favor the R form, the oxy form of hemoglobin, and this will increase the affinity of hemoglobin for oxygen. So here in low pH, there is shift of the curve to the right, and there is decrease the affinity for oxygen. And here where there is increased the pH, there is shift to the left, and oxygen leave the tissue to hemoglobin and increase the affinity of hemoglobin. The third factor is 2,3-biphosphoglycerate, which is important regulator for binding of oxygen to hemoglobin. It's one of the intermediate of the process glycolysis. As we said before, 2,3-diphosphoglycerate will favor the T form. It will cause right shift of oxygen dissociation curve. Again, what the meaning of right shift means that hemoglobin will give the tissue its oxygen unloading and decrease the affinity of hemoglobin to bind with oxygen. This will favor the T form of oxygen. Why it will favor the T form? As it this molecule of diphosphoglycerate will bind with the positively charged cavity in the deoxy hemoglobin and favor it. In the equation here is the oxyhemoglobin. In the presence of diphosphoglycerate, it will be converted into deoxyhemoglobin, which will bind to the positively charged cavity of the deoxyhemoglobin and will stabilize this form. This will decrease the affinity of hemoglobin of oxygen and release oxygen to the tissue. Rule of diphosphoglycerate in the tissue. The level of diphosphoglycerate will increase in the conditions of chronic hypoxia, in anemia, and in high altitude. This increase in the concentration will lead to shift to the right in the oxygen dissociation curve and leading to decrease the affinity of hemoglobin to bind with oxygen and release the oxygen to the tissue. In transfused blood, stored blood for long time, there will be decrease in the concentration of the diphosphoglycerate. So there is oxygen trap. That means that hemoglobin in the stored blood have high affinity to bind with oxygen. Why? Because there is low concentration of diphosphoglycerate shifting to the left, high affinity of hemoglobin to bind with oxygen, so the transfused blood won't release enough oxygen to the tissue. So in severely ill patient, they may be compromised if transfused blood have large quantity of diphosphoglycerate due to oxygen trap. There is no oxygen release or decrease in the oxygen release to the tissue from the stored blood. Here are the curve of diphosphoglycerate. There is here the concentration of diphosphoglycerate in the blood in high altitude will increase, leading to right shift of the curve. Here blood stripped from diphosphoglycerate. Stripped means there is no diphosphoglycerate like stored blood. There will be left shift of the curve and high affinity of hemoglobin to oxygen. Carbon dioxide, as we said before, increase in the carbon dioxide due to metabolism will be converted into bicarbonate ions, but some carbon dioxide will be connected to the N terminal of the hemoglobin, form what's called carbamino hemoglobin. This binding will stabilize the T form of hemoglobin or the deoxy form, which have low affinity for oxygen and will shift the curve to the right, and carbon dioxide will dissociate from hemoglobin in the lung and released in the breath. The last factor is carbon monoxide. Carbon monoxide binds tightly but reversibly, not irreversibly. So it can be reversed and can be treated. It binds tightly to hemoglobin iron, forming what's called carboxyhemoglobin. Carbon monoxide binds one or more of the 4 heme sites of the hemoglobin, leading to left shift of the curve. As we said before, was the meaning of left shift? That there is increase the affinity of hemoglobin to bind with carbon monoxide instead of oxygen, as there is a high affinity for hemoglobin, about 220 times greater than oxygen, and this will cause the remaining heme sites will bind with oxygen with very high affinity. So this hemoglobin won't be able to give enough oxygen to the tissue, and this will cause carbon monoxide toxicity. Even minute or minor concentration in the environment of carbon monoxide will produce the toxic carboxyhemoglobin, which have high affinity to bind with hemoglobin than oxygen, and will decrease the oxygen released to the tissue from hemoglobin, and this occurs in smoker. Carbon monoxide toxicity is treated by 100% oxygen therapy, which is called hyperbaric oxygen therapy. This is the curve. In the presence of 50% carbon monoxide, it will be in the form of hyperbola. In 0% carbon monoxide, it's normal curve. It will be shifted to the left here, hyperbolic, in the presence of carbon monoxide.